Good afternoon, everyone. I'm Yuhao from Southeast University. It's my great honor to be here to present our recent work titled Knowledge Graph-Based Quality Defect Traceability with with Reinforcement Learning. Uh, uh, my presentation has 8 parts as follows. There are introduction, motivation, research gaps, objectives, related works, and this study's methodology framework and its case study results and the conclusion and future work. And this is the first part, is the background. Quality defects are prevalent in building projects, such as cracking, low strength, dimensional deviations, growing voids, which may cause the safety risks, shorter service life, and higher costs. The second is the defects emerge from coupled cross-stage factors from design to testing feedback. And the third is the concealed defects appear only after components are covered. And the last one is conventional tracing is subjective and fragmented. Based on the background, we have the four research gaps. First is methods, static and experience driving, and the second is the life cycle data, not unified into one reasoning base, and it cannot rebuild a traceable causal chain. Last is the reinforcement learning fits path research, but is rarely tailored to defect tracing under engineering constraints and small data. So we aim to build a multi-level defects knowledge graph from multi-source evidence and formulate tracing as a MDP, then develop a DQ agent to search the chains. The related works have 3 aspects. The first is the defect cause and analysis. First is the from symptom to multi-factor mechanism. They are mostly static and expert driving. The second is ontology. The knowledge is as entity relation triples, but the instance-only knowledge graph is fragmented reasoning. So we want to use a multi-level, but because it has the better interpretability. The last one is reinforcement learning for knowledge graph reasoning. It's the saying the tracing like the sequential decision making, but it needs engineering constraints. This slide shows the this research's overall KGRL framework. From the first is the data can be input. There are multi-source evidence such as the BIM, IVC, or etc. And they are used to build the multi-level knowledge graph. Then it can it's the reasoning environment which are composed of the ontology, relation, instance, plus the engineering constraints. As the reasoning environment, the RL agent can traverse the knowledge graph. Lastly, it can output the two things. First is the rect plausible root causes, and then is the interpretable causal chain. And then I will introduce them in detail. First is the multi-level knowledge graph. It has 3 aspects. First one is the ontology layer. It is the standard vocabulary. They are about defect, component, process, and cause categories. It is built in Protage for semantic consistency. The second one is the relation layer. It is about the process order, thresholders, evidence alignment. The last one is the instance layer. It is from the real project evidence. Then based on the knowledge graph, the traceability can be seen as a MDP. It has the 4 four parts. First one is the state. The state is the KG node. It is encoded as a one hot vector. Then the agent can have an action. The action is to pick one feasible outgoing edge. The third one is the transition. It can move to next node until it stop at the end or the hop limit. The last one is the reward. Reward we have a 5 level from the terminal to the others. Every relation has different reward weights. It has the from the 7 to the 0. Based on the MDP, we use the deep Q network to do the train. It is a value-based policy via deep Q network. It outputs for feasible edges, and it is trained by minimizing the TD loss. As the DQN, it has three aspects. First one is the epsilon grady exploration, and second one is the experience replay, and the last one is the target network. After the training, it outputs the rect causes and interpretable passes. After the methodology, we do a case study. It uses in the real, it's a real Pi Foundation construction project. It has the it provides two aspects of data. The first is the early stage zone data, and the other is failure scenarios from repair records. Then we'll do the same thing. It's a knowledge graph evidence and the graph scale. First is the evidence. We got the evidence such as records, routing logs, curing, and the test reports. Then it was instantialized by our RDF type to the defect-centric graph. Then we did the constraints embedded. The whole graph has the 24 nodes and the 42 edges and the 11 ontology classes. Although it is small, but it's enough for preliminary validation. And the graph it can be trained as a DQN environment. After the training on the knowledge graph, we got the top three causal passes. The first one is the management condition to the site management ignorance to the cage displacement to the inadequate cover. As you can see, the three passes are all about the inadequate concrete cover. It is the key mechanism. Then is the evaluation part. In this case study, the hit at 1 and the hit at 3 are all about 1.0. It recovers the true expert investigation logic, and the curve shows that the reward converges to max, and the TD error becomes stable in the 2000. The last one is the reward design aligned with the engineering logic. To be concluded, the multi-level, we have three aspects of the conclusion. First is the multi-level KGDQN framework and consolidates the life cycle quality evidence. The second one is the DQN agent learns plausible multi-hop causal chains, and the last one is the interpretable traceability, can from the symptom to the root cause. Last is the real case. As for the future work, we have the 4 aspects of future work. The first is a benchmarking. We are about to add BFS or DFS baselines to qualify the DQN efficiency gains The second is the scalability. The graph embeddings such as the node to wake to build the curse of dimensionality. The third one is the validation, which we want to apply to completed projects for full process backtracing. And last is the reward objectivity. The data driving reward shaping to reduce expert subjectivity. That's all. Thank you for your attention.
Not that it's right.
Works?
Your validation proves that you could do it,
Yes, yes.
but doesn't show that the results are right.